Thank you again for joining us. We're looking at CAN communication on this vehicle. We did what I'm about to do in a previous video, but I wanted to start again looking at this using a feature called masks and alarms, which allows us to capture these intermittent faults with CAN. We'll start with the guided test, and under guided test menu we have communication network. So you'll see here that I can click on communication. We have 4 networks in total. 2 options for CAN bus actually. We can either go CAN bus physical layer, so that's just looking at packets of data, or we can go for serial decoding. I'm actually not going to use that. I just wanted you to be aware of it. We're going to set up CAN manually. So here we have channel A and B active. We're just looking at CAN high and CAN low. Now, the reason I'm doing this is I want to add something now called a math channel. So if I click on the maths icon here, we'll see something here called A plus B. That's what we're interested in because we're looking at capturing intermittent faults. Now, what is A plus B? It's CAN high plus CAN low. 2.5, 2.5 makes 5, 3.5 and 1.5 makes 5. So in the perfect world, you end up with a straight line, which tells me that CAN high and CAN low are performing as they should do. We can use that now to our advantage because if we introduce or we capture a fault on either CAN or CAN low, that 5 volts will be disrupted. As such, that is an indication to the user that somewhere on there the impedance or the circuit has changed. So we'll set up something now called a mask, which actually captures an intermittent fault on CAN. What I'll do, I'll just click on our software. We can drag these waveforms just out of view, and I will then change the scaling for the math channel. So we'll put the math channel at something ×2, and the reason being I can bring that down to around 5 volts in the viewport, in the scope view. Now we click on a feature called mask, and we'll choose which circuit or which channel we want to mask. And we're going to go for A plus B, and we'll go for generate mask from source. Apply the mask, and you'll see there that we have a mask drawn around our 5 volt signal, our math channel. And notice in the bottom corner, I'll just make this large so as it's easier on the eye. We've got our number of passes and number of failures. So passes are buffers. This is where CAN high and CAN low have passed through the buffer without a fault. And failures are where the mask has been intruded upon. Everything is looking good at the moment. We have no failures on this CAN network. Now, this is a great opportunity for the technician to go into the harness, wiggle testing, moving, pulling on plugs, etc., trying to almost shake a confession out of the network one way or another to produce the fault. On that, we also want to be notified. So we could introduce a fault now, we will capture it, but once the buffer is full, we'll actually miss or lose the fault. So we'll add something called an action to our mask. So we want to go to actions, we want to change the events. So on mask fail, we want to stop the capture, and we want to play a sound, and that will just be a bleep. So let's summarize. CAN high plus CAN low is 5 volt. As long as those voltages stay within that, those parameters, everything's fine. If it doesn't and it steps outside, it will intrude into our mask. If it does intrude into the mask, the software will stop, which means it will capture the event. This is hands-free, and it'll also play a sound to notify the user. So what I'll do now is I'll introduce a fault onto CAN. It's only a momentary fault, and there we have it. That was no more than shorting, I think it was, CAN low down to ground. So I've had to do nothing there. Now that could have actually been me anywhere on this vehicle. certainly thinking about the stuff that Ben works with, some of these trailers that could be 40 foot long, there's no way you can be anywhere near the PC. So to be able to be at the back of the truck and listen out for the bleep and then come back, there you have it. And just to tally, or just to actually clarify and clear what's happened, let's hide the mask. In fact, what we'll do, we'll delete the mask. So, sorry, we'll delete the mask. We'll take away the actions, and we'll actually take away the math channel as well. So we'll turn the math channel off, and now we'll look at these signals. We can clearly see there how we had can high, can low, as it should be, plus 2.5, and then 3.5, 2.5, 1.5. Then all of a sudden in this area here, can low, definitely short to ground, wasn't it? In fact, look at the disruption there. And let's just pull a ruler down so we can see what happened. Yeah, we're as good as 0 volt at that point. So we're happy we captured a short to ground on can low. So a nice hands-free feature. We covered that in the previous video, but we've gone over that again because it lends itself nice now to moving on to the additional features of Pico, which is reverse engineering. Okay. So we'll run PicoScope and we'll start again. We now want to do something called serial decoding. We want to sort of find out exactly how the packets are made up. We want to pick out things like the IDs, the acknowledge, any flexible data that might be in there. This isn't CAN-FD, but it may be that you're working on a CAN-FD system. So let me just clear that out the way. This time, we're going to use a different math channel. We're going to use math channel A minus B. Now, what does A minus B give us? Let's have a look at this. A minus B gives us the differential voltage of the CAN network. So this is the actual physical layer that the computers, the nodes, are looking at and interpreting for data. It's also a good way of removing noise, because if there's noise on CAN high and there's noise on CAN low, which there should be, then the differential, one cancels the other out. What we end up with, let me just stop the scope here, is 0, 2 volt. So I'm going to zoom in on this packet of data here. Just grab the hand tool, and there we have a perfect CAN packet, almost textbook. There's two together there, isn't there? Yeah, 0, 2 volt, the differential CAN voltage. Right. So with the differential voltage, we can now choose, if we wish, to decode. So we'll open the decoder that's built into PicoScope. So we have serial decoding. Now, note the amount of decoders that we have. There are 4 there, actually, CAN-FD, CAN-XL, and CAN-J1939, thanks to Ben's work in decoding that. We have just conventional CAN on this, or classic CAN, I think they call it. So we click on CAN and click Next. It's asking which channel do we wish to decode on. So it's A minus B. We want the math channel. Next is the threshold on which we wish to decode. Excuse me. The threshold on which we want to decode. We'll go for 1 volt, purely because the math channel is 0 to 2 volt. 1 volt is perfect in the middle, so that's our great crossing point. Hysteresis, that allows for noise. There doesn't really appear to be too much noise on here. We'll go for something like 100 millivolt. We know the baud rate on this is 500 kilobaud. We can actually measure that. I'll do that in a second, so we can actually prove, first of all, what is the speed of our network, so we can actually apply that into our decoder. Click Next. We want to display, in the graph view, hex. We can hex, binary, or ASCII, whichever it is, and the same in the table format. We'll go for hex in both. A good tip here, rather than decoding 50 buffers, we'll decode the current buffer. Excuse me. And that is because if you look in the top here, in our waveform navigator lozenge there, waveforms, we've got 50 waveforms at the moment. I'm only really keen or interested in decoding what's on in the current buffer. So we'll decode on current buffer. One other option, and this can be helpful when you're searching for events in the CAN packets, in the train of data. It may be that you want to decode in a certain area where something else happened in the time domain. You can decode between the time rulers. So you've narrowed it down from 50 buffers down to the current buffer, and then you can narrow it down further still by just decoding between the time rulers. We'll leave that off for now. Click Finish, and here is our decode table. So you see here now we have our packets numerically ordered, start time and end time of each packet, the IDs, the RTR, FDF, flexible data frame, the data length. The packets, here we have ID 280, 8 bytes within a packet. DRC, excuse me, the CRC, it was acknowledged, CRC was valid, bit stuffing was valid, it's a valid packet in total, and ID is set to 0. The fact that that is written in black means that is a good packet, we're happy with that. And if I wanted to zoom in on that, if I just double click, it takes me straight to that packet within all that data. So rather than go searching for it and zooming, etc., we can go straight to ID 280 with that payload and have a look to see where that may have failed, if it had failed. Which brings me on to, how do you find a failure? So we can, let's click on valid. If I click on valid here, in fact, what are the chances everything in there is decoded correctly? Oh, no. I think I saw something red there. Let me try that once more. So valid. Okay, what about acknowledged? Okay, well, let's introduce a fault. So we're now actually decoding live, you can see that. In fact, something that Ben talked about was views. If I click on this here and drag this to the side, we'll be able to have our waveform on the left and our decode table on the right. Let me just bring that in. So we've got the entire table. Well, let's introduce that short circuit to ground momentarily and just see what happens to data. Now, I'm sure within there, we should have captured an error or introduced an error. I did see it on one of the buffers, so I can go back through the buffer. There we have it. So you see here right at the beginning, let's zoom in. There was an event where the CAN packets were disrupted. So there's disruption there, which must, says he, resulted in an error. So let's have a look. So by valid, okay, let's go for acknowledge. Surely not. Okay, well, let's have a look why that was the case, because we can actually see the pack. Let's just zoom in right at the beginning. I mean, this is testament to fault-tolerant CAN, isn't it? That there I am putting a momentary short on the network, and yet that did not result in a failed packet. No, okay, well, I'm not having it because I'm going to make that work because it worked in rehearsal. Let's do that once more. So let's go for a short, a momentary. Yes, I saw it. So not only did I see the short, but I saw the actual packets of red data. So let's go back. There we are. And we can see there that a number of entries into the table are red in color. So if I wanted to know where this packet was, this is ID 5AO, has come back as not acknowledged. Double click on that, it takes me straight to that packet of data. If I pull out a time ruler, just place it, let's say at the start of that packet, and then let's zoom back out, close the zoom, we can see where we are with the ruler in the whole graph view, so we haven't lost our way, and it looked like it was towards the end of the short circuit where we had that error packet. So really powerful tool. I mentioned about trying to find out the speed of the network. So if you don't know the speed of the network you're on, I mean, this is powertrain CAN, so it will be 500 kilobit per second. If it was something like convenience, well, all we have to do is measure the smallest bit within a packet. So if I go for something like this here, this normally comes out about 2 microseconds, something like that. Yeah. So he's praying for a steady hand. Okay, we could zoom in closer and we can see just how far away I was, miles away. Yeah. Okay, so two microsecond divisions, that gives us a baud rate, or certainly a frequency of just shy of 500. There is no CAN network at 490.2 kilohertz. It's 500 kilohertz frequency, 500 kilobit per second. So it's a useful tool to know how to determine the frequency of the CAN network that you're working on. Okay, so reverse engineering, that's where we wanted to go next. So we'll keep the settings as they are. Remember, we're decoding on the math channel A minus B. I'm going to slow this right the way down now. Ben talked about this earlier. This was something called block mode and streaming mode. You'll notice now how we're in actual streaming mode. Let me just change the sample rate, because the sample rate does not need to be that high. That improves resources, doesn't it? So you'll notice how channel A and channel B are being streamed live. In other words, we're seeing them being drawn in real time. You'll notice also how the math channel is updated at the end of the buffer, because maths is only carried out or actioned at the end of the buffer. So there is a little bit of a delay before the math channel is updated. The decode table is only showing us all the failed packets at the moment. So why is that? Let me go from the start. There we are, because not every one of those could have failed. Right. Reverse engineering. Now, we happen to know on this vehicle that the ID for our ABS ECU is 1AO in hex, so 1AO. So we can search for that. We've got search tools here. We'll click on the search icon. The field we want to search on is the ID. The operator is it contains, in other words, we want it to contain the following digits, which is 1AO. You'll notice now the decode table is only showing 1AO. So that's great. Everything there, we're still collecting all that data. All other IDs are still being collected behind the scenes, but we can see that 1AO is the only field we're filtering on. What I wanted to do now was just simply disconnect the ABS ECU. He says it like it's easy, and it is. It should be. It was working in rehearsal. Let's say what happens when we're filtering for 1AO. So at the moment, 1AO is present on the network. So I'm just going to pull the connector off the ABS ECU. Make sure we've got separation. And now notice, it's not really that clear on the left. Certainly the bus traffic has dropped off. It seems to be there's less traffic. But now 1AO does not appear. There will also be other IDs that don't appear, because not only is 1AO from the ABS, there will be other ones. I think there's 4AO, 5AO, 6AO. Nevertheless, a quick way of determining whether or not 1AO is online. So if I erase the filter, now we're getting all the CAN traffic as we had before, but 1AO is not present. Okay. Now if I reconnect, now that, if disconnection was difficult, oh, there we are. There we should see 1AO appear again. I can see it there. And then just to confirm, if we go back to the filter, contains 1AO. Yeah, it's back again. All right. It may be that you want to discover or learn what other IDs are associated with this 1AO and ABS ECU. So let's first of all stop PicoScope. You have an option here to export data. So we can export this data to CSV. So everything that you see in the decode table now, we can move across to CSV, and I'll just call this Audi export. I should have called that Ford export, shouldn't I? Should have, yeah. Sorry. And click Save. The beauty of that is now you've got all the features of Excel. You can import the CSV into Excel, and then you can start using all those features, sort of removing duplicates, or looking at data packets, or maybe just filtering out certain IDs, certain packets, so then you can graph data. So again, another powerful feature of the decoder that you can then manipulate in third-party software like Excel. So there's also a way of actually IDing or turning this data into human readable data. So we happen to know that 1AO is ABS ECU. So why not have that appear in the decode table as ABS? So what we can do here is we can click on the create template. So we create the template, and I'll call it again. I'll call it Audi template. And we'll save that. Now what we can do, we'll go back to that template, which I'm hoping is here. There it is. We'll open that and we'll give the ID 1AO. We'll give that a description of ABS and click Save. So that's a very simple, quick way of identifying ID 1AO. It may be that you want to go on and do far more with that, because you can give a description to a certain byte, whether it's road speed signal, whatever it may be. You can start giving full descriptions to the data, almost like a DBC file. So save, close that, minimize. Now what we can do, we can, excuse me, open the template. So click on Audi template. That will pull in the template, and let me remove the filter. Now where you saw 1AO, you will now see ABS. So there we have it, look, see, packet number 3, rather than saying 1AO now, it says ABS. So in human readable form, we know that that packet is from the ABS ECU. We could also filter. You'll have to change the filter criteria though now, because that will have to say ABS. So let's add that. And now everything ABS is displayed there. So that's all 1AO. So we're only now in all this data, and let's run this because we can run this live. We're only collecting data from the ABS ECU. Which then brings me on to the data packets. Now, just note that in the data field, we have 0047, and it's that second byte that I wanted you to keep an eye on, because the plan is now to actually press the brake pedal, because I know either through reverse engineering or DBC that byte 2, by changing one digit, actually represents brake pedal position on or off. So the plan here, and I've enjoyed doing this actually, was to operate the brake pedal, which is a physical connection. In fact, I've got the wiring diagram here. So if you look at ABS in this diagram, you'll see that the brake pedal switch, which is S13, is hardwired into the ABS ECU, which is A16 here. That signal is then transferred and placed onto the CAN network via the ABS ECU. And I was intrigued to find out how long that actually takes, that process from the physical power supply from the brake pedal switch coming into the ABS ECU, being then placed onto the CAN network. And I guess I should get out more, shouldn't I, really? But it does excite me, nevertheless. We need to add more channels. So what we have now is the brake pedal switch connected to channel C. So we'll pause Pico. Channel C, it's BNC plus, so it's plug and play. And over and above that, I've also got channel D, which is a current clamp. We'll come to that in a moment, but let's just have a look at, well, first of all, let's configure PicoScope. So channel C is connected to the brake pedal switch, which is a 12-volt signal. And channel D is a current clamp, wraps around the CAN wiring. One of the CAN wires, I think it's CAN low, yeah, CAN low at the ABS ECU. What I found really useful, and Ben has done a great video on this. He's actually using our current clamp to determine who is sending the signal and when. So because it's going to the ABS ECU, when the ABS ECU transmits something on the CAN network, we can catch it with the current clamp. And we'll prove that now. We have to make some tweaks here because there is a lot of noise on this signal. So first of all, we are 500 milliamp. We want to add some filtering, so we'll make the filtering active. So you'll see in a second that at the end of the buffer, notice how channel D just minimizes. In fact, let's clear this display up because we don't need to see a lot of what's on channel at the moment. Because we've got the math channel, we'll take away, using the views feature, channels A and B. They're still being captured, but we don't need them. The current clamp, we want to amend the scaling on there, and I think the scaling on this was something like times 10. Okay. We'll run PicoScope, and it looks like a car crash at the moment. We'll wait till that gets to the end of the buffer. Okay. And let's get some separation. When I zoom in, you'll notice that we have packets of data where the current is positive. Now this is as a result of a transmission from the ABS ECU, and we can prove that. So if I zoom in further still, we should start to see that these packets here, if I hover over them, 1AO. Remember, 1AO is from the ABS ECU, as is 681. So let me just place a ruler at that point there so we know where we are in all that data. Close the zoom. So at that point there, we know that that positive current above that line, let me zoom in again, is data coming from the ABS ECU. So it's a great technique when it comes to actually just seeing if that ECU is online for one, because if it's online, it will be transmitting, and then we'll be able to determine from current flow. Remember, you need to be on a branch for this test. That works well. We've actually on a, rather than be on the trunk of the network, we're actually on a branch. If that network is going down for whatever reason, it'd be good to monitor the current to that ECU, because if that's the ECU that's responsible, you'll see a peak over and above typical CAN traffic. So it is a powerful tool. Right, so what I'll do, I'll take away channel D because it really does consume. And now we'll just run PicoScope, looking at brake pedal signal. So I'll put a trigger on this because we want to capture the time that the brake pedal goes from on to off, or off to on, I should say. And where is our trigger? Our trigger is going to be a repeat trigger on channel C, and we'll put it to a threshold of something like, in fact, this is confusing. There we are. Right, so at the moment, no data is being collected. The trigger is waiting for the brake pedal switch to go from off to on, so it'll go from 0 volts to 12 volts, and at that point, we'll capture the event, the analog event in the time domain from the brake pedal switch, but also all the digital data from the CAN network. So yeah, if we can just press the brake pedal on and off, Ben. Remember, our decode table on the right is going to display ABS. Off. Can we go faster, Ben, sort of on and off? There we go. All right. So let's pause that. And let's go back through the buffer. So there we have CAN network data, brake pedal switch going from on to off, and at some point during that process, the event, brake pedal off to on, had to be transmitted on the CAN network, but where? So the quickest way is to go down. Remember, byte 2 is brake pedal, so we're looking for a transition where the bytes go from 4.7 to 4F. There we are. So at byte 650, the state of the brake pedal switch had not changed. When I go to 4F, it had changed. So I'm going to place this ruler here. Where were we? 1804F. And come back out of the zoom. So my packet number, let me find that again. I've lost where I was. So from 47 to 4F. 47 to 4F was 9.3, yeah, just over 9. 47 to 4F, 9.328 milliseconds after the trigger. And let's prove that. So our ruler is at the start of our packet of interest, where byte 2 changed. It's the trigger that is our 0 point. Sure enough, 9 milliseconds after the brake pedal switch went from off to on, it was then reported on the network for the rest of the network to interpret. So yeah, there's a lot to take in there, but knowledge of the CAN network, if you've got a DBC file, that's great, but that's using PicoScope to really zoom in on analog events and then capture them also in the protocol, in the CAN network, in the digital domain, as it were.